Hey everyone, so welcome to the first video in Unit 3. We're finally there. And this is a big unit, has a lot of different concepts, but today we're going to really focus on one core concept and actually the relationship between that concept and a different concept. The core thing that we are talking about today is work. And this is a very important concept in physics, and so we're going to spend a good amount of time just understanding what work is, because the calculations aren't super complicated, but understanding what it is a challenge itself. Specifically, we're going to deal with work as it relates to another concept, which is the concept of energy. And we're not going to discuss much about energy in this video. This is going to come in future videos, but we are going to discuss the relationship between work and energy, because it's a very kind of symbiotic relationship. They kind of interact a lot. So first we're going to talk about what is work and what is energy. One thing you've probably learned in physics is that a lot of physics words have more specific definitions than we would use them in real life. And we learned this last unit when we were talking about forces. We all had this knowledge of what a force was in daily life, but physics had a very specific definition of force beyond what we might have thought of as being a force. And it's the same thing with work and energy. So let's start by just thinking about what is work in our daily lives. Well, when we talk about work, we usually mean things that we do. We go to school, people would consider that some work. If you have to move houses, that's work. If you're doing yard work, if you're gardening, that's work. If you're cooking, you could say that's work. If you have a job, of course, that's work. They're kind of things we do in our life. And what is energy? Well, it's kind of the thing that our body has that we use to do work. And you could create some kind of sentences. If you don't have a lot of energy, you can't do work very well, or maybe even not at all. And also, if you do a lot of work, your energy goes down. And these things are true in physics as well. And in fact, work and energy are interrelated in that they kind of have their definitions intertwined. You can't really define one without the other. Basically, we say that energy is the ability to do work, and that work is something which changes an object's energy. So these are defined kind of in terms of each other. So neither one can be kind of figured out alone. You need both. So remember that. Work changes energy. This is the role of work. It's a change, it causes a change in energy. Remember how force causes a change in velocity, or it caused an acceleration? Work causes a change in energy. Energy is the ability to do work. And this is kind of the core concept, and so take a second to appreciate it. Work changes the energy of an object, and energy is the ability to do work. If you have no energy, you can't do work. If you have energy and you do work, the energy will be depleted. And then if you have none, you won't be able to do it. Kind of in daily life. If you have a hard day, you're tired, your energy's been exhausted, you can't do work. Now, we're just going to specifically talk about work today. And remember, work changes energy. And like everything else in physics, we measure work quantitatively using a unit. And the unit of measurement is called a joule. This is the measurement. Not a joule like this, but a joule like that. Joule. And joules are the unit of measurement that we use to measure work, just like we use seconds to measure time, and just like we use meters to measure displacement, we use joules to measure work. The unit is represented with just a J, so you could say like 10J, and that would be like 10 joules of work, for instance. And the way you calculate joules, or J, is by taking the dot product of two other quantities. We learned about dot products in the math skills video last time, so if you have no clue what I mean when I say dot product, check that out. But we do this by taking the dot product of two values, and it's force and displacement. This is the equation for work, and work is W, which kind of makes sense, and this is the equation we use. Work equals the dot product of force and displacement. And this is pretty useless because, remember, we don't really know how to do dot products, but we can remember that the dot product expands to this. We learned this again in the math skills video, so I recommend going there if you're confused. But this is the real equation for work we are going to be using. Work is equal to the absolute value of the force times the absolute value of the displacement times the cosine of theta, where theta is the angle between the force and the displacement. And I'll show you an actual example so you kind of see what this means afterward. Now, there's only one important thing to note about all this I'm talking about, like the equation and how it transforms. This only works when force is constant. Force must be constant. If it's not constant, this all falls apart. This equation doesn't work anymore. We need a different set of more complicated equations, and in fact, we need the concept of integral calculus, which is a great university-level math concept. We're not going to be dealing with that. We are going to deal with some questions where force is not constant, but it's going to be very limited, and you're going to do it by graphing instead of using any math. And I'm going to show you that at the end. For the vast majority of questions, you can assume, or it'll probably say that force is constant, and when force is constant, this is the equation for work. Work equals dot product of force and displacement, which is absolute value of force times absolute value of displacement times cosine of theta, where theta is the angle between force and displacement. Okay, now we're going to specifically look at some facts about work, specifically how there are 3 different types of work, we would say. And this might seem a little confusing. What are types of work? All I mean is there's different things that work could be. You can have positive work, and literally this means a value where work is greater than 0. You can have negative work, which is pretty obviously a value where W is less than 0. And you can have 0 or no work. And that is obviously when W is 0. And there's a couple interesting things about each of these and how they can occur. And so I'm just going to go through these really quickly. To have positive work, you have to have a force that is not 0. It needs to not be 0. Because if you have 0 force, you can look at this equation and notice that if you have 0 force, it's going to multiply 0 times all this and it won't matter. It's just work will be 0. So to have positive force, force can't be 0. Also, displacement cannot be 0. And the angle theta, is going to look like this. I'm just going to draw this and then explain it. The angle theta needs to be less than or equal to 0, greater, than, and or equal to 0, and less than 90. That means it can be anywhere from 0 up to 90. So it can be 0, it can be 1, 2, 3, etc., all the way up to, but not including 90. So it goes up to like 89.9999. That's how that goes. This is a less than or equal to sign. This is a less than sign. So it's saying that 0 is less than or equal to theta, which is less than 90, which means that theta is between 0 and 90. Hopefully that made sense. The object's energy, when you have positive work, will go up. It'll increase because positive work means the object's energy increases. That might seem counterintuitive to daily life where work always makes energy decrease, but in physics, positive work means that energy increases. Let's look at negative work. Negative work happens in most of the same conditions. You also need a force which is not 0, and you also need a displacement that isn't 0. So these two values still cannot be 0, but the angle is different. Now it is between 90 and 180. It can't include 90, but it can include 180. So if you are at 0 all the way up to 89.99, you're dealing with positive work. If you have 90.1, so you're above 90 all the way up to and including 180, you're doing negative work. So what's the one condition we didn't meet here? Well, it's 90 degrees exactly. That's neither positive nor negative. Let's explain the next category here, which is 0 work. So 0 work, what's happening here? 0 work can actually arise from 2 separate things happening. So we're going to kind of make 2 separate sections here. You can have 0 work if you have a force that equals 0. Or if you have a displacement that equals 0. And why this is true is pretty logical. Back to our equation. If displacement here is 0, then this entire thing that you're multiplying together will be 0, and work will be 0 straight away. The other alternative for 0 work is that you have force and displacement that are not 0, just like before, plus, and you have a specific angles. These specific angle is 90 degrees or negative 90 degrees, and negative 90 degrees is also 270 degrees. Why is that true? Because if you look at a circle, that's a terrible circle, but it's fine. If you have 0 degrees here, and here's 90 degrees, and here's 180 degrees, here's 270 degrees, and you're back to 360, while going positive 90 and going negative 90 is the same as 270. So if theta is any of these values, and only then, you have 0 work, or if either force or displacement is 0, you have 0 work. This is the most important thing here. You need to make sure that you're always dealing with a situation where you understand that you're dealing with positive work, that you're dealing with negative work, or that you're dealing with 0 work. This is always the first thing you should identify. Do I have no work, do I have a negative work, or do I have a positive work? Okay. It's also worth noting that there is a concept of net work, which is exactly like net force. And it's literally just adding together all the work on an object. Same deal, adding together all the forces. Net work is something we'll see. I'll also point out that if you've been dealing with this, you'll notice that work is not actually a vector. I have not been doing W this. Work is a scalar. It has no direction because the dot product takes two vectors, but it gives you a scalar that has no direction. And so work is just a value. It's a normal number that we've dealt with since like grade 1. There is no direction to work. Okay, I'm going to finally end this by kind of showing you a concrete example and then by showing you one other thing. But let's do a concrete example first because I feel like that's always helpful. Here's a floor right here. That's, my typical excellence in drawing. Angle up here. This is like an incline, so like, some sort of hill or something. And there's a box here. Here's our box right there. And someone's going to apply a force. This is a force right here. And it's going to be a force, and it's going to be 10 newtons. And there's a displacement here that the force caused. It's a delta D equals, I don't know, let's say 10 meters delta D equals. So you notice you have a force here, and you have a displacement here. And force and displacement are the two things you need to get work. The only other thing you need is this angle of incline. And I'm going to show you something that students commonly would make a mistake on. Here's basically how we would calculate this. We start by saying, okay, work equals, and we remember that we need absolute force, absolute displacement, cosine of theta. So let's do it. Well, we start with absolute force, and we know that force is 10 newtons. 10 newtons of force. We have absolute displacement, and we know that displacement is going to be 10 meters. And so I'm actually going to use brackets instead of absolute, and the reason I'm doing that is because I'm making them absolute by not putting a direction. This is technically 10 meters in a specific direction, like that direction, but we're not going to do that. I'm just putting this, so I've made them absolute by removing the direction components. The last part of this would have been cos theta. And here's where things are going to get screwed up. What is theta? A lot of students would go ahead and notice the 25-degree angle here and be like, oh, well, that's theta. And they'd put cos 25. And that seems right, but it is not right. And the reason it's not right is because 25 is the angle of incline, which is a value that you might need to know in some cases, but not for calculating work. For work, the value that you need is the angle between force and displacement. So what is that angle here? That angle is actually 0. And you know it's 0 because force and displacement are going along this same line here. Force is here. Displacement is here. all along the same plane. If your force was instead coming in at an angle like this, for instance, and it was going this way, and so you had a force here, you would now have an angle between the displacement and the force that you would need to calculate, and that would be theta. But in our example, there's no angle, so it's cos of 0. You could do this calculation now, and you would get the work for this body given this force. Practical word problems, as usual, will come a bit later, as long as you understand these essential concepts of work and how it relates to energy. The last thing that needs to be covered here is one kind of fringe topic that you're not going to talk about a lot, but is worth mentioning. And that's this basic concept of what if the force isn't constant. Because remember I said force needs to be constant to use that equation. Well, in that case, you're going to be dealing with something that you have to solve by graphing, because you don't know and aren't going to for a bit what integral calculus is or how you would use it. So the focus right now is graphing. And a lot of the work is going to be done with you, for you in the question. The thing you need is something called a force displacement graph. And it's a graph where this axis is force and this axis is displacement. And you're not going to have to create this. You'll literally be given it in the question. And let's say it looks something like this. Obviously, will not be that complicated in the question. I don't know. Let's give you actually a simpler example. Let's say it looks something like this. Okay. So here's your force displacement graph, and you need to find the work done here. This formula does not help you anymore. The cosine, the absolute values, not helpful. What you instead need to do is determine the area between the x-axis, that's this thing here, and the curve. So you essentially need this area. And we've done this before when we're converting between, if you remember, displacement time, velocity time, and acceleration time graphs. You've done this before where you found the area under a curve. You're going to do it again here, and you would break it down into 4 different quadrilaterals in this case and add them together, and that would give you work. This is going to be a very fringe question. They won't happen a lot, but you need to know how to deal with this very basic case of force that changes across the displacement. That's pretty much all there is to know there. So let's zoom out and kind of look at the whole thing. In conclusion, work is a thing that changes energy. Energy is the ability to do work. We've talked about how when force is constant, we can use this equation here, and you're going to be using this an awful lot. We've talked about net work. We've talked about the different types, positive, negative, and 0, and which angles correspond to them. And we've talked about an example here and how to identify the correct angle between the displacement and the force, not just the angle that happens to be in the diagram. We've talked about the rare case where you're dealing with differing forces over the displacement, and this kind of sums it all up. We also talked about joules, the unit, and how we're going to use those to represent work. And that's the basis of work. You're going to do a lot more questions with work, and they're going to become more complicated when we introduce energy, but for now, as long as you understand these basics, you'll be good to go. Hopefully this was helpful. Thank you for listening, and I'll see you guys soon.